In this tutorial, we will see how to work with the multiple server waiting line model. This tutorial builds extensively off the single server exponential service time model, so it is critical that you review that tutorial first. Many situations involve multiple servers. For example, grocery stores, department stores, toll booths, and TSA checkpoints. These models can be very complex. This tutorial will cover only the most basic of these models. Even the simple model is more than what is covered in most courses, so check with your instructor before proceeding. The assumption for the multiple server model are the same as for the single server model, only with 2 or more servers. 1. There are multiple servers which we assume to have the same operating parameters. The number of servers is represented by the letter S. 2. There is a single waiting line that is common to all servers, such as you might find at a TSA checkpoint or the post office. Models for multiple lines, like you might find at a grocery store, are much more complex. 3. Customers are selected based on arrival time, with the first to arrive being the first to be served. 4. Arrival rates can be described using the Poisson distribution. 5. Service rates can be described using the exponential distribution. 6. There is no practical limit on the size of the waiting line. These calculations involve factorials, a mathematical technique not covered elsewhere in these tutorials. A factorial is represented by an exclamation point. 0 factorial is defined to equal 1. 1 factorial is defined to equal 1. 2 factorial is 2 times 1 equals 2. 3 factorial is 3 times 2 times 1 equals 6. 4 factorial is 4 times 3 times 2 times 1 equals 24, and so on. Factorials are only defined for non-negative integers. They get very large very fast. In fact, most calculators that handle factorials can only handle factorials up to about 70 factorial. For this tutorial, we will not need a factorial larger than 4 factorial. The equation on the screen calculates the probability of there being no customers in the system. Notice the use of the summation symbol on the bottom and the use of S, which is the number of servers. For 2 servers, for example, you would compute the value in the square brackets for n equal to 0 and 1 and add these values together. Also notice the use of the factorial on the bottom. These 2 equations give the probability of there being n customers in the system. The equation on top is for when asking about a situation where there are more customers than servers. So, for example, with 2 servers, this equation would give you the probability of there being 3, 4, 5 or more customers in the system. The equation on the bottom is for when the number of customers is less than or equal to the number of servers. In this scenario, all of the customers would be receiving service and none would be waiting. You cannot use this equation for the probability of there being no customers in the system because that is one of the terms needed in this equation. The remaining equations are shown on the screen. The URL shown on the screen is for a website that will automate these calculations for you. Simply click on the Select Model for M/M/C option and enter the required information, namely lambda, mu, and the number of servers. Note that this website is not under my control, so I cannot guarantee it will remain available or be correct, but I did test it and always got correct results. Also note that this is to check your work, not replace your doing the work. In this example, a branch bank specializing in complex commercial transactions has 12 customers arrive per hour on average. These customers wait in a common line. A teller can service an average of 5 customers per hour, and there are 3 tellers. Find the steady-state parameters for the queuing system. First, a quick check of capacity. Each teller can service an average of 5 customers per hour, and there are 3 tellers, so the system has the capacity to service an average of 15 customers per hour. At an average arrival rate of 12 per hour, there is adequate capacity. Had S times mu been less than lambda, the system would develop an infinite queue and none of the equations would have worked. You plug in 3 for S, 12 for lambda, and 5 for mu. On the bottom, the part in square brackets gets calculated for n equals 0, n equal 1, and n equal 2, which is 3 minus 1. When n equals 0, that part of the equation equals 1. For n equal 1, it equals 2.4, and for n equal 2, it equals 2.88. 1 over 3 factorial equals 0.17. 12 divided by 5, all raised to the 3rd power, equals 13.8. The last part of the bottom inside the parentheses equal 5. The entire equation evaluates to the probability of 5.6% that there are no customers in the system. The remaining calculations are shown on the screen. Pause the video and examine these in detail. There are, on average, almost 5 customers in the system with an average of almost 2.6 waiting to be served. The average time in the system is 25 minutes and the average wait is 13 minutes. There's almost a 65% chance that a customer will have to wait for service. For this example for you to try, the bank manager wishes to know how much the system will improve if she hires a 4th teller. Since you've seen an example already, let me suggest that you pause the video and try to work this problem on your own. Once you're done, you can use the video to check your work and spot any mistakes you might have made. Normally, we would begin by making sure that the queuing system had adequate capacity. However, we know from example 1 that the old system had adequate capacity, and this example simply adds additional capacity, so we can skip that step. Adding an additional server increases the probability of the system being idle from 0.056 to 0.083. That small of an increase was to be expected due to the long waits the system was having with 3 tellers. Rather than increasing idle time, the 4th teller is mostly reducing the wait. The number of customers in the system drops from an average of almost 5 to 2.831. The number waiting drops from an average of 2.589 to 0.431. Average wait time drops from 13 minutes to slightly over 2 minutes, and average time in the system drops from 25 minutes to about 14 minutes. If this video helped you working operations management problems, please consider liking the video and subscribing to the channel.